Good morning to you all. Madam, Anita ma'am. Ma'am, please unmute and try one time, ma'am. It is.
Hello. Good morning, everyone.
Good morning, ma'am.
Good morning, sir. Good morning, everyone. It gives us great pleasure and honor to welcome Dr. Ishan Badri, Research Fellow at the Institute of Transport Studies, University of Leeds, UK. Dr. Badri is a highly respected scholar in travel behavior modeling, econometric analysis, and emerging mobility systems, with a strong commitment to promoting sustainable transport and decarbonization strategies. He completed his doctoral research at the IIT Kharagpur, where he explored the behavioral impacts of ride-hailing and shared mobility services. His work employed advanced econometric and machine learning techniques to understand how these innovations are reshaping urban travel patterns. Dr. Bowdry's research has been widely published in reputed international journals and presented at prestigious national and global conferences. By integrating artificial intelligence, big data analytics, and behavioral science, his work provides invaluable insights into how people travel and how cities can adapt to meet future mobility needs. We are indeed privileged to have him with us today to share his expertise on travel behavior modeling and his critical role in shaping intelligent and adaptive transport infrastructure for the future. Please join me in extending a warm welcome to Dr. Ishan Badri today's session, sir.
Thank you for the warm welcome. Am I audible?
Yes, sir, you start, sir.
Okay, okay. Thank you for the warm welcome. And yeah, it's been privilege to be here, to be among my fellow colleagues. And thanks for the invitation from Dr. Sai Priya for this great opportunity. So I'll share my screen. Just let me know if you can see that. Can you see my screen?
Yes, sir. Yes, sir.
Okay, okay. And feel free to just call me Ishan. It's completely fine. No worries.
Yes.
So I've made it full screen. I guess you were able to see the full screen now.
Yes, yes, yes. Yes, sir. Yes, sir. Yes.
Okay, okay. So before I start, I think it's a 2 hour long session, and I'll be mainly talking about the topic, as you can see, the application of data science in travel behavior modeling. And maybe we can take a small around 10 minutes break at the point of 1 hour tentatively, if that's fine with the organizers.
Yes, sir. It is totally fine, sir.
Okay, okay, because I thought maybe at 2 hours at a stretch might be too
Sure,
much
sure, sure.
hectic for the people to grasp the things.
Yes, sir. Yes, sir. Yes, sir.
So, as I already said, thanks for this opportunity. And today we are going to talk about how we are kind of experiencing more and more application of data science, be it big data or be it various techniques like machine learning or deep learning or large language model, nowadays artificial intelligence in the travel behavior modeling. And to start with, I'll give a short introduction. I think already Anita has given a very nice introduction about me, but just to kind of reiterate, uh, who am I, what are my interests, what I'm currently doing. So I'm presently I'm in currently Institute for Transport Studies at University of Leeds and currently working as a postdoctoral research fellow. In UKRI funded Nexus project, where we are doing travel behavioral modeling with help of various large scale passive data set, for example, social media data set or mobile GPS data set. And we are using currently various techniques in terms of deep learning or even large language models to understand how we can leverage those data sets to gain more insights about the travel behavior, how travel behavior evolved over time. Of course, when we have this kind of large scale passive data set, there are also some issues which I'll be covering throughout our discussion or our presentation today. And in terms of my research interest, I'm mainly interested in travel behavior modeling, econometric modeling, future mobility system, for example, autonomous mobilities or urban air mobility. And at the same time, I'm quite intrigued to research and know about their emission and energy impacts, and specifically in the context of this global south or developing countries, as we call them, with an aim to finally reach to a transportation system which are equitable and sustainable through evaluation of different policy measures. So yeah, today's presentation structure, I have divided it into three parts. The first part will give you a brief idea about the domains of the application of data science in transportation planning at large, and then also within travel behavior modeling. This is the focus of today's topic. And we'll also give you a very brief overview of various machine learning techniques that's been used and what are their use cases. Part two and part three are two case studies that I've been working recently, and that will give you a very clear idea about the methodology of application of this kind of techniques, as well as what kind of data set we are using and what kind of insights we can gain when you leverage this kind of methods. So without much ado, I'll start with the first slide for today's presentation. That's the application of data science, which is increasing, which has been increasing over past few years in transport planning. So I'll start with transport planning because that is kind of the bigger domain. So whoever we are interested in understanding the transport better, as a, for example, from a planner's perspective, it's quite important to understand what are the domains where this data science, big data, or these techniques can be used. These are the examples, which these are very prominent examples, like traffic flow prediction. You can get millions of data set from the link level flows of vehicle, which you can use to understand or forecast congestion and travel time along those links and better optimize the network. Second one could be like optimization of public transport network. We all know that in Indian cities or at large in developing countries, it's quite a problem sometimes to adjust the schedules and also the fleet management, which results in delays or very high waiting times, and that in turn results people avoiding public transport, buses, for example, which make it more like not so sustainable in case of cities. So that can also be done with help of this large data sets. Then infrastructure planning, like what kind of new roads or new, say, metro lines that we need. So our decision has to be evidence based. So in case of the traditional models, we always go for the survey-based data sets, and but which is very cumbersome in terms of time and in terms of effort, in terms of money to collect. But with help of large data set, like large mobility data sets, you can get a very good idea about what are going to be the potential demand for various infrastructures. And another example could be smart traffic control. We all know that in cases we sometimes develop, say, for example, green corridors, or sometimes we need to better optimize the network. So you give priority to more sustainable modes. For example, in the BRTS system, the BRTS buses will be given priority in traffic signals. So that kind of smart traffic control all over the network can be done with help of real-time data set about the link level flows or traffic flow information. So out of this, I'll mainly focus for the example said infrastructure planning. And as I was giving the example of demand for a particular mode, which will govern whether you need a new infrastructure or whether you need to adapt the existing infrastructure or not. So that part brings us to the travel behavior. And within travel behavior, what we can do, there could be like four key things. For example, the first one being the mode choice prediction, like what particular travel mode person will choose based on his or her context, based on the infrastructural context, based on other social context, based on the attribute of the alternative, for example, travel time, cost, waiting time, flexibility, departure time, route. The other one, which is derived from this mode choice, is the travel demand modeling to understand this mode choice and translate it to understand the travel patterns and volumes over various transportation links. The other examples could be, for example, these personalized travel assistants. We are nowadays very much acquainted with Google Maps or different kinds of similar apps, which gives us the idea about the best route we can take, for example. And finally, the other example could be behavioral insights to, for example, to understand what are the factors that influencing this choice for the people. For example, I am choosing metro over car, but I will not choose bus over car. So, what are my reasons? Although both bus and metro are public transport, my reasons could be, for example, that metro, the waiting time is very low. It usually sticks to its original schedule. It's quite fast enough, and maybe comparatively, the time cost trade off, it is cheaper enough, so that might influence me to take metro over car. But in case of bus, I might find the reliability for bus is not enough, or the within inside bus there could be very high crowding, or the seating arrangements or sitting comfort or convenience is not enough for me to avail bus over car. So that could be my reasons to take metro over car but not bus over car. So these kind of insights we can gain with help of a large data set uh, to understand how people are choosing their modes to reach from one origin to their destinations. So I will, by the way, before I delve deeper, um, I think I'm open to any questions, but if organizers have any specific way of conducting this, then I'm also fine. For example, I can take questions in between, or is it like should we do it at the end?
So, shall we do it at the end, sir? So
Okay,
it is
okay, no
better.
problem. Okay, no problem. Thank you. Um, so now we have got brief idea about what are the application areas that was important to understand why we are here as a transportation professionals. Now we'll get some idea about a brief overview or idea about the what kind of machine learning techniques or broad machine learning techniques that are being used currently to understand this travel behavior. So we can categorize the machine learning techniques broadly into three categories. The first one being supervised technique. As the name suggests, it's learning the pattern with help of labeled data. So when you say labeled data, that means you are saying that data point A is say good, data point B is bad, and there will be thousands of data points like that, and you'll be having say training the model with help of say 100 data points. So for 100 data points, you'll say these 70 data points are good, this rest 30 data points are bad. So your model train based on what you feed into the model, how you train into the model. So that is we call as label data, and the technique is known as supervised machine learning technique. The second one is unsupervised. So again, the name is quite intuitive. So unsupervised means you are not training anything to the model. Rather than you are giving the model, say, look at this 1,000 data points, try to find some underlying pattern or structure, and then return with those underlying structures or groups that you can identify out of this data. So you do not have any training data set or label data set. You have the whole data set, and within that, the machine learning techniques try to find the clusters who are more similar to each other rather than who are more dissimilar to each other. And in this way, they find the underlying groups or clusters within the unlabeled data. And the third one is reinforcement learning. So it is like teaching the model with help of rewards and penalties, as we say. So I'll be discussing it in bit detail in the following slides. So let's start with the supervised learning. So as I just explained, supervised learning mainly involves training models. So it is like more a teacher-student relationship, as you can see, that you are training the model. You are saying these are like 70 good data points, these are 30 bad data points, or rather say in terms of good or bad, we might understand it differently in engineering, where say that these 70 are red balls, and then you say rest 30 are blue balls. So you are kind of training the model with help of your own label, and then you ask the model to do the same exercise for you for the rest of the data set. And that's the main idea, that you might have millions of data set, but you need to train the model with a say very small data set, what we know as training sample, say 1,000 data points, and then you ask the model to do it for the rest of the data set. That means for the millions of the rest data set. And obviously, as we can understand it intuitively, I'll say that you have more number of training data points, your model starts getting better and better, because then the model can learn from the experience that, okay, I classify all this as red balls when they have this kind of features, and I classify all of them as blue balls when they have this other features. So you train them with say 500 data points instead of 100 data points, your model starts getting better. So as I just explained, there's label data and then the model training of that. And then the main thing is that role of input and output mapping. The input is the label data or training sample that I am feeding into the model. Then the model generates a very clear mapping of this input feature to the target output. What is the target output in the example that I gave? So it is like classify it as a red ball or a blue ball. And then it tries to create very accurate predictions based on these training samples. That's how supervised learning works in machine learning. So within supervised learning techniques, there are broadly two categories. The first one is the classification, and the second one is the regression. So we'll also go through the examples very quickly, like what are the use cases of this supervised learning techniques. So, but before that, what is classification? Classification is that when your outputs are in different distinct classes or categories. For just similar to the example that I gave. So instead of now say two colored balls, think there are five colored balls, say red, blue, yellow, green, white, like that. So, but these are each of them are distinct categories, right? You can count them, they are countable. So there are five categories. You are training the model to say, okay, we have 70 data points, which are red balls, 30 as say blue balls, then you have others say 20 as yellow balls, or another 20 as green balls, but these are all countable. So that's what we call as discrete class or category. So this technique where your model learns to classify them into various classes or categories, we know this technique as a classification. So what are the real life examples? Real life examples could be detection of spam emails. So we are very much now acquainted with these spam emails of this kind of emails in our inbox, quite a few. Sometimes our profiles or our Gmails uh, get hacked. So we have the algorithms, all these Google and other companies, they use this algorithm because you might have seen that you get these notifications from them that this message looks quite suspicious or it's quite fishy, is likely to be a spam email whenever it comes to Google. And sometimes you know that once you train or kind of classify one email as spam email, so it always goes to your spam folder. And sometimes Google itself sends some fishy email directly to your spam folder. So how uh, does Google do it? It's an example of this classification technique that they train their own algorithm in a way that based on certain features of the emails, it can classify them as a probable spam email or a normal email or general email. So what could be the features? For example, we know that in a normal email, we kind of have we add proper salutations, or we write our names to the people we are sending, then we end it with say best regards or kind regards. So there are some formats. Also in terms of when we write, there is a kind of tone and proper language that we use to send our formal emails, or also for the personal emails there are certain patterns. But in case of spam emails, you'll find there are certain kind of trend. So they will ask you to click on a link, for example. They will offer you maybe some extravagant amount to get something done. So there are those trends which kinds of gives you an idea that this is spam email. This is something very similar to what we think as a human being in our mind also. Like whenever we see an email, so by nowadays we are kind of uh, aware about various spam emails or this kind of fake forward messages on WhatsApp. So now by now our brain is also trained to understand, okay, how does a fake message or how does a spam email look like. So this is the same thing. The algorithm also trains based on this few actually spam or emails or fake emails to understand what are the features of those spam emails, and then it uses it to understand the spam emails for the future one, like it classify the future emails as spam or not spam. Of course there will be some mistake. It can't be 100% accurate, and that's the reason sometime we all say that can you please check that whether my email has gone to your spam folder or not. So why does it happen? It simply happens because sometime maybe we have written that in a way uh, which might make it look more like a spam email. So what Google does, Google's algorithm directly thinks that it is a spam email and put directly into the spam folder. So this is an example of classification technique. The second one is that, say in real life, there will be many other things which are not or which cannot be classified as categories or classes. For example, take the example of predicting stock prices. So stock prices means it's not we cannot classify it, say it's a five types of stocks. There are different types of stocks, but I'm talking about, say, for take an example of one particular type of stock and how it prices goes up and down in the market, say over 1 month. So it's a example of a continuous variable. So whenever we want to predict a continuous numerical value, we use this regression supervised technique. So in terms of say drawing an analogy to the statistical technique, this is very same as the regression we all know. So the linear regression we have all studied in our bachelor's. So that's what also used in case of supervised learning. We for the continuous numerical value, that's the regression one. So within classification now, I'll give you a few examples of the exact technique. So classification is the name of the broader umbrella of techniques. So within that we have various particular techniques which are used to classify the output into different classes. And I have added them in order of added complexity from top to bottom. So the first one, that's logistic regression. That's is very uh, similar to what we know as logistic regression from our statistics, and it can classify it uh, the when the output variables are, for example, just two in number, like we call it as a binary classification. Also we know multiple logistic regression, where you, if you have more than two classes to predict, you can use that too. Other than that, we also have, say, decision trees. So decision trees are more like a tree like model, and where you have each of the branch which kind of represent the decision rule. What is a decision rule? Decision rule is, say, if I take the example again of red ball and blue ball. So decision rule is that whether you classify this as red or blue. So that is one decision rule. That's a very simple example of decision tree I'm saying. And then each of the leaf node that we call represents the outcome. So decision is red or not. So if yes, it's a red ball, that's a decision that comprises the leaf node for that decision tree. So we always interpret in a tree-like structure, and it is known as decision trees. The third one is the support vector machine, which uses that optimal hyperplane. I'll explain why you call it hyperplane. But before that, so it optimizes a hyperplane that best separates the data points for different classes. The most important thing is the high dimensional space. So as I was giving examples, so not necessarily we're always classifying between two or three classes. There could be multiple classes. There could be, say, 50 classes. So in case of 50 classes, I cannot plot them in a two-dimensional, not even in a three-dimensional space, right? So this is a very high dimensional space. This is basically for 50 classes, I have 50 dimensions. So for that high dimensional space, so if it would have been just two classes, I would call it a straight line. But since it is in high dimensional space, we call it as hyperplane. So the target for support vector machine is to find this optimal hyperplane that gives up that best separates these data points to make them understand that they are from different classes. In simple words, it means that how to best categorize them in a red ball and blue ball categories. So that's example of binary. So say in the 5 case example, red ball, blue ball, green ball, white ball, and black ball. So that's example of support vector machine using the hyperplane to differentiate between classes. The another one is the k nearest neighbor, where the value of k is given by the analyst. That means when we are modeling this k nearest neighbor, we give them the value of k, and it's a simple non-parametric algorithm which helps to classify the data points based on the majority class of its k nearest neighbor. So as the name suggests, so it's more like based on the principles that birds of the same feather flock together. What does it mean? It means that I am more likely to be part of a cluster or a group of which I'm very close to. So if you think in real world terms, so if we hang out with a particular group of people, it is more likely that my nature is kind of similar to those people, and that's why we are hanging out. That's why we are uh, kind of syncing with each other, right? So it also follows for the examples of data science too, that when you have a data point which is close to a cluster, it is more likely that the data point is part of that cluster rather than the data point is part of another cluster which are far away. So k nearest neighbor does that. So say one point is close to three classes, but what are the closest one it has? So that we call as the majority class. For example, one data point is close to two classes. One class has 10 examples and the class has five examples or five data points. And this particular data point is closer to this one cluster with 10 data points rather than those five data point clusters. So I'll say this point is more likely to be part of this 10 point cluster. And that's what we do as k nearest neighbor. The last example is the random forest, which is similar to the decision tree, but more advanced version of decision tree. And that's we call it an ensemble method that builds on multiple decision trees and combines their predictions based on majority rule to improve the accuracy and of course reduce the overfitting. I think the term accuracy is easily understandable, but we might not be aware about the overfitting term. Overfitting is what we call, so when we are training the model. So I have now almost said it quite a few times that how we train the model based on the few data points, 100 data points. But there is a chance that since you are training the model or teaching the model based on the existing pattern of the data, there are chances that you are also modeling the noises as actual data points. So you're training the model what it should not learn. What does that mean? For example, that we all know that whenever we model something, there are outliers or noises in our data points. So when we model, that's why we call them outliers or noise. So that doesn't uh, go or that doesn't fit well with our understanding or with the rational behavior. But when you are training that with help of data, not based on theory. So how we understand these are not fitting with our rational behavior? Because we have our theory based models, say economic theory or some other theories. So we say that based on these theories, this particular data point doesn't look plausible. It might be because of other reason or might be simple because it's an error. But when you do not have any theory, you're completely going based on the data set you have. That's the way data science or data scientists approach the problem. You might not understand that this is a outlier or this is an error or noise. So when you are trying to teach the model so much that it tries to fit it even to the noises, that we call as overfitting. So overfitting is not good because noises are not real data. But if you fit your model to these noises, then when you go for predicting with help of your model, your predictions will not be very good. Because for good predictions, we need to have a more generalizable model. That's our criteria. We do not need the model to fit exactly with the training data. We need to have a model that fits well with most of the data points, not only with the training data. So overfitting is simply when you are trying to make it very well fit to the training data, say 100 data points or 1000 data points. But when you are predicting for the millions of data, it is not performing as good. So with that, I'll go to the second supervised learning technique, that's regression. So within regression, the first one is the simplest one. That's the linear regression, where we find a linear relationship between input feature and the output. So I guess we are already now aware about various. We already have at least aware about the input and output. What is what? So I'll maybe I'll give an example of house price. Say. So how does the house price change, or what are the factors on which house price depend? So at least when we go to find the prices for this new apartments, we know that it depends, for example, on the carpet area for that apartment, types of amenities, uh, types of other factors, for example, how closely it is located to the bus station or the metro station or bus stops, or whether you have other services within the compound or not, whether it is ground floor or first floor. So these are all the we call as features or factors which influence the house price. So in this case, these are all input features, and the output feature is the house price. If it is a linear relationship, that means that when the house price say is y, and then these input features like the carpet area, like the extra services you have or the amenities you have, these are all x1, x2, x3, and they are linearly related. It's not that y is related to x square or y is related to root over x2 like that. So if it's a linear relation between input features and the output, then we use a linear regression, which is the simplest one. But at the same time, as you might understand that in real life, it is not always used, because in real life we do not have linear relationship between input and output always. So that's why we have the second technique, that's the polynomial regression. So it's a form of linear regression in which the relationship is modeled as nth degree polynomial. So it is exactly what I was just saying, that the relationship does not necessarily need to be linear. For example, say that based on the proximity, like how close your house or apartment is to the metro station, it increases the price, but it might not be linear. For example, if it is 500 meter, then the price is 1 lakh. If it is 250 meter, it is 2 lakh. That's linear. But it could be because for every 100-meter reduction, the price might go up 3 times. And then again, if it is just 50 meter, it might go up 5 times. So it is not a linear relation. It could be more complex than that. For example, it could be that the price relates with the square of the proximity distance. Or it could be that, for example, we all know that for the carpet area, it might increase very highly for up to a particular limit, but after that, it might have a stable increase, not a very exponential increase. So maybe up to say 2000 square feet, you will find an exponential increase of prices, but maybe 2000 to say 5000 square feet, you find it is not exponential, it is some other type of curve that the price is following. So that is what we achieved through the polynomial regression technique. Now moving to the second part. So if you remember that we started off saying that we have three categories: supervised, unsupervised, and reinforcement learning. The second part is this unsupervised learning, where, as I said, basically you are not training the model. The model will perform on its own. You are just supplying the model with data points. And when you do not have any label, that is what we call as unlabeled data. And why and when is it used? It is used for to find the hidden structures or underlying structures. So underlying structure means that maybe there are millions of data points. With our human brain or human eye, we might not be able to differentiate between them or find there are 5 clusters hidden in it, because they might not be hidden in a 2D plane. So human eye or human brain cannot perceive much beyond 2D or even not even 3D sometimes. So it is quite difficult to understand or to extract that structure. But with help of this unsupervised learning, we can find that there are 5 clusters. Maybe these 5 clusters are hidden at 10 dimensional space. So that is what we can achieve through unsupervised learning. So going to the techniques, there are mainly two types of techniques that uh, are used for unsupervised. The first one is clustering, and the second one is dimensionality reduction. So clustering is what I was exactly giving the example. So these techniques group similar data points into clusters. I guess it will be more clearer when I'll give you a real life example. Say these marketing companies, we're all aware about getting phone calls from insurance companies, or say car manufacturers or other sales companies. So do you think they call each and everyone? No, they create a very targeted marketing strategies based on which particular group of people they will target. And when I say group of people, this grouping can be done on many factors. For example, this could be done for based on age, based on income, whether they are urban people, rural people, uh, whether they work in a particular type of company, like that. For example, to sell a new mobile, this company will target maybe say a young person with average to high income, with maybe who is a very tech savvy person. So it will not target say a old person who is not much into these new gadgets. So that's what we understand when we say we need to classify the population into various groups. So but it is when we have this multiple factors, say, excuse me. So when you have these multiple factors, say age, then income, then say gender, and where they live, urban versus semi-urban versus rural, so there could be 100 features like this, and it is not easy to classify the groups when you have hundreds of features. That's where unsupervised techniques can help you to identify what will be your target group. So what will be that group which kind of ticks off each of them? Like they are young, they are say average to high income, they live in rural areas, say they are male. So like that, that is what we can achieve through clustering techniques. And same thing can also be done for grouping news articles or similar topics. So you could actually do it yourself too. If you just go to the Google News and you just type the keywords, it will give you a set of news which has those keywords in it. So it actually uses this kind of inherent clustering mechanism to find that whenever you give them those criteria or feature, it gives you uh, those news which are clustered based on the keywords or criteria that you have given or supplied to the Google News. The other example use of unsupervised learning technique is for dimensionality reduction. Why is it important? It is important for the same reason we are talking about, just the purpose is different. The reason is same. That means that we have hundreds of features that we do not know, but I cannot tackle hundreds of features in my model. So I want to develop a model for the house prices, but I do not know what are the factors uh, which affects it. So let's take the house example, but with a change in it, that now I'm not interested to know about the features exactly. Rather, I am just interested to know which house prices are high, which house prices are high to medium, which are medium to low, which are low, like that. So what I can do, I can say supply this all the features together, and I'll ask the unsupervised to give me some broad features which might not be meaningful, but which will be a kind of simplification of 100 data points which I can use at later stages for my analysis. So basically reducing the 100 features to say 10 most important features which I can use in the subsequent analysis. The use example or use case for it is like compressing images, or say simplifying the large data set. That's the example I was giving about the house prices. Like we have 100 features, we can uh, get it down to the 10 most important features which can be used. So that makes your life easier basically. Same goes with compressing images too. And the one of this example is that whenever we say we just upload our files to say Adobe or other this compressor, they basically use this technique simply. That's the underlying mechanism that makes them to compress the PDF from say 50 MB to 20 MB, because they are uh, trying to maintain the broad quality of the images. But maybe you'll find that when you're compressing the images, the image which is being generated is not as clear as the original one. Why does it happen? It simply happens because it is reducing the dimensions, the internal dimensions for that image. Same thing is done when you are compressing the PDFs too, that it reduces the internal dimension, but it keeps the most important ones. That's why you can still read the image, you can still understand the text, but you will find the quality will go down broadly, but that will not affect your ultimate goal. Rather, that fulfills your goal to have a small size PDF or small size image. That's how unsupervised learning helps us. And as we did for the supervised learning, we'll also talk a little about the particular techniques that we use. So within clustering, one is called as k-means clustering. So in the supervised one, we talked about the k nearest neighbor. Here also the k means something, the value of k is what you will supply, but in terms of algorithm it is different. So k nearest neighbor was classifying the data points in a particular class based on the majority class. But in case of k means clustering is that you give it that say there are three distinct clusters. So it will iteratively assigns the data points to the nearest cluster centroids to classify them into these different clusters, and then it recalculates its centroids every time so that it gets updated and new data points are being added to one of these three classes. The second one might also look similar to what we learned about decision trees, because in hierarchical clustering it also creates a tree-like hierarchy of clusters, and then it can be done either in a bottom-up approach or divisive approach that's top-down. So in decision trees, for example, we are talking about branching from top-down. That's what we call as divisive approach. But in hierarchical clustering, it can also be done as a bottom-up approach too. The second one, the very prominent example of dimension reduction is the principal component analysis. So what it does, it creates a new coordinate system. So what does it mean that it's a new coordinate system? For example, if you try to understand, we all must be acquainted about the, say, three-dimensional axis, for example, X, Y, and Z axis. But now, as I was saying, there are 100 features. So you cannot plot 100 features into three axes, right? You need to have a new coordinate system. So it creates that, but if you still say that I want it to plot into three axes or say three clusters, then you need to reduce the dimensionality, that 100 dimensions, into three dimension. How is that possible? That you create this new coordinate system where each of the axes is a linear combination of this 100 axes. So that means each of the axes is a linear combination of some of these features, what we known as principal component, like this new axis. And why we say principal component? Because in principal component, these axes are ordered in a way based on the amount of variance they capture within the data set. And for example, the first principal component is always the one which captures maximum amount of variance. And then in the decreasing order of this variance capture, we create these other principal components. So the final technique that is the reinforcement learning. And as you can read that the reinforced learning mainly mimics the decision making by rewarding reactions. Sorry, rewarding actions. So what does it mean? That it is very similar to what you can say as the learning through trial and error. So where we use reinforced learning, one of the most common example of reinforced learning is the usage of say robotics. And you might have heard about these robot dogs, which are now being used by the armies, military operations. So, for operations of these robot dogs, when you are trying to train these robot dogs, for example, to find out explosives, so how does it train them? So, it is like you train the robot dog, you have some explosives, uh, it goes there, it detects it as an explosive, so you reward it that okay, it has detected it rightly. Maybe there were no explosive, but it still detected it as explosive. That means it's a wrong detection, so you penalize it. So after one trial, it understands that how it has rightly detected explosive and got rewarded, and if it has not rightly detected the explosive, it got penalized. So after one trial, it got either reward and penalize, and based on this reward and penalty, it understand what is the correct detection is. Maybe in the second round, there were some explosives, but it could not detect them, or there were no explosive, but it still detected it as an explosive. So based on this multiple rounds of trial and errors, and for each success you reward them, and for each failed attempt you penalize them. So based on this cumulative rewards and penalties, and with an ultimate aim of maximizing these rewards, it learns how to detect a particular objective. In this case, I gave the example for the explosive. It could be anything else. For example, the same thing is also used for this unmanned aerial vehicle or this autonomous vehicles too, to understand, for example, rightly understand if there is a pedestrian on the way, so it should decrease its speed, or it should put the brake on, like that. So for this robotics, autonomous vehicles, urban air mobility, these kind of reinforcement learning are used. So maybe we'll take a very short break, and then I'll talk to you about two case study examples that I have been working on, where we have used various large scale passive data set. The first example is where we used social media data sets, particularly Twitter data set, to understand how public perception has changed over time and across various countries towards urban air mobility. I think you will find that interesting. And till now, if you have any questions, feel free to ask, or maybe we can also do it at the end. I'll keep some time. But for now, maybe take a very short 10 minutes break, if that's fine.
Sir, yes, sir. We'll take 10 minutes breaks. After that, we'll start this
Okay,
session, sir.
thank you. Thank
Thank
you.
you, sir. In this, participants to are request to share your feedbacks about this 5 days FDP, sir. So you will take rest, sir. I'm just discussing with participants, sir.
Yeah, yeah, sure, sure. No, yeah.
So I'm unmuting to all the participants just to share your thoughts and about this FDP. I unmuted everyone. If anyone interested, anyone want to share about the feedback of these sessions, or not only in the sessions, the previous sessions of the 3 days we conducted. Yes, sir. Actually, I unmuted, sir. If you unmute yourself and discuss, sir. I give a permission for everyone. If you anyone want to, please unmute yourself and discuss.
Sir, this is Dr. Anandu.
Yes, sir.
from Sedu Institute of Technology.
Yes, sir. Yes, sir.
Associate Professor from Sedu Institute of Technology, Tamil Nadu, India, sir.
Yes, sir.
The organization committee is highly organized and perfect manner you are conveyed the messages, and that also same followed. I'm very happy with this thing. And then the chief guest you are called are highly effectively shared the messages, and the high profile persons only you are chosen from the schedule onwards. I've noticed that. So I got a lot of information from the presentation of the dignitaries, and then I'm happy to be a part of this session.
Thank you, sir. Thank you,
And
sir.
then regarding this session also very good given lot
Sir, actually, your voice is
of
breaking, sir.
information regarding sir.
Sir, your voice is breaked, sir.
Give me a minute, sir.
Good morning.
Yes, sir. So, good morning, sir.
Myself, Dr. Rajiv Chauhan. I am working as associate professor in Punjab Technical University. It
Yes.
is one of the state technical university established in 1997. I found this FDP very interesting, and the topic is also need. What is required by our teachers to the generations, civil engineers. Only one summation is that we should focus on one more thing, that the slope stability, landslides, and earthquake seismic, how we can implement practical data in machine learning. That can be a further ahead for the next FDP if you can plan. By the way, from my side, it's very good, and I'm entirely satisfied with this. Thank you.
Thank you, sir. We are taking your input. Next FDP, we are incorporating that geotechnical things in our FDP, sir. Sure, sir. Thank you, sir.
Now voice is clear, sir.
Yes, sir. Yes, sir. Yes, sir.
Okay. The sessions are very good, sir, and then they are given a lot of information, sir, regarding that the graphical information. From the graphical information, we will get a lot of information from the previous classes, sir.
Yes.
That is yesterday class. I got a lot of information, and then today's session also he's given a lot of information regarding traffic management, other things.
Yes,
Okay.
sir.
The sessions are very good, sir, and then the organizing committee, I'm highly appreciate you peoples. Thank you, sir.
Thank you, sir. Thank you, sir. Thank you, sir. Sir, and one more thing I'm requesting, we are posting a YouTube link also, sir. If you know further things, you can take that YouTube link as a notes also. We will share the record things in a letter, sir. But if you are urgently needed, so you can take that YouTube link as your things, sir. It will be available in YouTube, sir.
It's in text message, sir. Where you
Sir?
shared? Where you should share?
If you share
Sir.
a link to that concerned mail, then good for us, sir. So
Sure,
that we will
sure, sir. Sure, sir. Sure, sir. YouTube
that-
link will share. Actually, in a group, always we are sharing every sessions in a YouTube link also.
So
Okay.
actually,
Live,
we are
live.
not in that WhatsApp group, I think.
So okay, sir. You could have personally text me, sir. I will add you, sir, there.
Okay.
Sure,
Okay.
sure, sir.
Through mail also, if you are sharing, means it's useful
Yes, sir.
for
Yes, sir. When we are providing the certificate, that time we will provide all the YouTube links with you, sir.
Okay, good, sir. Thank
We
you.
have that plan on that one, sir.
Very good, sir. Thank you, sir.
Thank you, sir. Thank you, sir. So, any other feedbacks from all the participants?
Sir, is it possible to send a mail? That time, is it possible to give a contact numbers of the experts who is spoken in our session?
Yes, sir. Actually, in
Phone number and
every session they provided their mail IDs and phone numbers,
yes,
sir.
sir.
So
But
if it is on
summarize,
YouTube, link, yeah,
summarize
we'll do.
while giving details, you will share the same through
Sure,
mail,
sir.
then
Sure,
useful
sure,
for
sir. Sure,
us.
sir.
Okay.
Sure, sure. Mm. So anything, any other participants want to share any of the feedback about this FDP, so 5 days FDP? if you are want to share, you can unmute yourself and discuss, sir. Actually, we are open to everyone now, because there is a 5-10 minutes break only. So for that only, I'm requesting your inputs is more needed for us to go over the next FDP with this lot of information things. We will come up with this new ideas of machine learning in which all the topics in the next FDP, sir. So your input is needed for us also. Actually, we have the two more sessions is there. Today's afternoon and tomorrow's morning session is there. Tomorrow morning we have a little bit of hands-on training sessions we are planning of, because the resource persons want to give the little bit hands-on training. Already ma'am has discussed in the group of to download this Google Earth Engine and they create the account of this one. Not download, create the account of this Google Earth Engine. Sir is planning to give a little bit of hands-on section on tomorrow's. So if you all be cooperate, it may be a little more good for us on this tomorrow sessions. And today afternoon one more session is this. After this, within 10 days, we'll provide all the certificates to all the participants within 10 days. We'll share your in your mail ID. We'll share your certificates and this link, the notes, everything's. So this is our request from our organizing committee. Tomorrow is Sunday. I know very well it is a little bit hard for everyone to attend this FTP, but a little more of this academic schedule, a little bit of constraints we planned on this holidays also. Uh, so if anyone, all the peoples, I hope understand, and tomorrow will be a good interactive session, sir. This is the request from our organizing committee. And one more information is within 10 days, you all will receive a certificate, sir. So it means that Sunday is overing. Then before the next Sunday, we'll all provide our certificates to you, sir, through your mail IDs. Mm. I'm posting now the WhatsApp link also. Whoever not in the WhatsApp links, please, I'm requesting to join in that WhatsApp link. Uh, before itself, we posted one more time, but again, we are posting this WhatsApp link. Whoever is not there in the WhatsApp links, please, I'm requesting to join in that WhatsApp link for the further FDPs and further events which we are conducting. We will update you, sir. We are planning of this December one more event in AI, truly AI with this machine learnings.
If possible, sir, try to have some physical mode, because you see online some possibilities are there. We keep on engaging in day-to-day activities.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Try
Actually,
to
we are so
if you get
interested to
AICT
conduct in
funding.
offline modes. Yes, sir. Yes, sir. Yes, sir. Our institution is also providing the funding for this conducting FDPs. So there is no restriction between to conducting offline. Definitely, we'll conduct the next session with this one, sir, in offline mode.
And is it possible both the sessions are online and offline together?
Yeah, sir. Actually, we planning that one only.
so that
Uh,
if
some
we are
people
having
can join in offline. Actually, we have all the facilities in the YouTube live on this radio stations, and all the things will be there. Definitely, will provide with us all the scenarios in the hybrid mode, sir. The next session, next FDP, sir.
so that possible we will come physically. Otherwise, also possible to get a message of yours
Yes, sir. Yes, sir. Yes.
while you
Yes.
be in online. It's useful for us to get a message while
Yes, sir.
traveling and getting both the
Yes.
session. If it is keeping, then it's good. Someone of the members who's near to us, near to your institution, then they will directly come to your. And
Sure, sir.
for
Sure,
us,
sir.
we are far away for traveling on the to take time. So that is a thing.
Sure, sir. Sure, sir. Sure, sir. Um,
Maybe we can
any other
restart
feedback?
now.
Yes, sir. Sure, sir.
Or
We'll
it's
start.
fine if you want to get some feedback.
No, sir.
So
No, sir. I'm just engaging if you are.
okay, okay, no
We'll
worries.
just
Sure.
we'll start. We'll start.
Okay. Just quickly check. You can see the full screen, right?
Yes, sir. It is.
Okay. Okay. Um, so I think I already gave an introduction about this topic where we used large scale social media data set to understand how public perception about the urban air mobility, which is also commonly known as flying car, changed across various countries across a long time frame from 2010 to 2021. So let's start with what are the current research gaps, what motivated us to do the research about this thing, and how we use this large scale Twitter data set. So presently, whatever studies we have now related to these futuristic modes, be it autonomous vehicles or urban air mobility. So when we are trying to understand whether people will adopt these modes or use this mode, it's basically or largely it is based on the use values. For example, values of time, be it travel time, waiting time, like that, and then the non-use values. For example, about the attitudes and perceptions of people. But there are certain gaps here. First of all, these are largely based on the survey preference approach, or rather we can say stated preference approaches, which are cross-sectional in nature. That means you only get information about, say, 100 people or 500 people at a particular data point. But we all know that people's attitudes and perception changes over time. So in India, say 10 years back, for us, bullet train was not even close to reality. But now we can think about bullet train, which are very close to reality. So it change over time. It is not something very constant. Then sample size. So when I'm going to this survey-based approach, I can collect the data from say 1,000 people, 2,000 people, but more than that, it's quite difficult, and it might not be a very representative idea about the whole population in India. Thirdly, we have the survey bias because whenever I'm asking you a specific question, your answer is going to be pivoted or hinged to that particular question. So, for example, if I ask you that whether you think these new modes will be fast enough or it will save you time, so you might try uh, starting to think about whether it is actually going to save you time. You might not think about the other aspects. For example, it might be very high in cost. So your response might be biased if I'm only following the survey based approach. And as I was just mentioning, this public perception is not a constant. So first of all, it changes over time. I gave the example of the bullet train, and also it is different across different parts of the world. For example, a person in India will not think in the same way as a person in the USA. So we all know about these studies. Most of these studies are USA based. So we cannot use those findings directly for countries like us. Like we cannot say that if people are very much enthusiastic about this autonomous vehicle in the USA, the Indian people will be the same, because the context is very different in India. We need to have a very context specific knowledge. And there we feel that social media data could be a good alternative because it provides these three distinct advantages. First of all, we could collect a very large scale data. I give you an idea about the scale in the subsequent slides. As we collected large scale data over a long period, so we collected almost over a period of 12 years, less survey bias based because of the reasons I just explained, and of course it's easier to collect and cheaper because we got this data set as part of our academic exercise for free from the Twitter. So in terms of methodology, so before delving to the exact methods, I'll first explain what were our aims and how we designed the methodology to fulfill that aim. The first aim was to understand the spatial and temporal, that spatio-temporal heterogeneity in sentiment polarities, like how much people are positive or negative or neutral about these new or futuristic travel alternatives. The aim was, of course, to understand the potential global market for this, whether this flying car, autonomous vehicles, whether they will be a successful venture in the context of India, or whether they can be successful but not at particular point, maybe 10 years down the line. So to understand the potential global market, it is important to understand what people think about these modes, what are their opinions about this mode, whether they're going, because that will give you an idea whether, and if yes, then when they're planning to or they're going to adopt this futuristic mode. Second one is the understand what drives this public opinion about futuristic modes, because that is important to understand what kind of new policies we can implement so that we kind of promote or we kind of also lead to a sustainable adoption of this futuristic mode. So for the first aim, we use the sentiment analysis, and within this sentiment analysis, we used at first stage various machine learning and transformer language models. So within machine learning, we found support vector machine to perform best, and within transformer, we found the BERT model to function best. And once we got the sentiments, we performed spatiotemporal analysis of the sentiments with help of the time series, which did the temporal part, and the k-means clustering, which did the geographical part. So with help of the sentiment analysis, we knew about how the sentiment changed over time and across various countries. But as I just said, that is not enough. You can understand, okay, in India, say in 2012, people are not very much positive about these flying cars, but over time and over various policies, for example, drone policies and other policies, people are now aware about these modes. They are maybe more open toward this mode, so they are more positive. But the still, what we do not know that what made them positive. For example, I just gave you the example of drone policies. So that is what I extracted when I performed dynamic topic modeling with help of these tweets. So once you know how the sentiment changed, people became more positive, more negative, or other changes. What made them become more positive or what made them become more negative? That is also important. That is what dynamic topic modeling gives us with help of first the context-based categorization and then analyzing the content with help of this large language models. So these are the full methodology, I'll say, just to give an idea that I explained you the crux of the methodology, but before you can perform sentiment analysis, since it's a tutorial kind of session, I also wanted to give an idea that it starts with when you're using this kind of social media data set, first it starts with filtering the tweets, for example, based on language or keywords, and also based on the countries. And the very important step is the data pre-processing steps, which mainly includes 4 sub-steps. Those are data cleaning, then tokenization, then removing the stop words, and finally stemming and lemmatization. To give you a quick idea about the size of the data set or the richness of the data set, as I explained, we have 12 years tweet data set starting from 2010 to 2021. And then in terms of the geographical variation, we have the tweets approximately 15,500 tweets across 6 countries. And there we have 4 countries which are English speaking, for example, United States, Canada, United Kingdom. Then lingua franca is the example of our own India, uh, where we use English as the official language. And then countries like Germany, where English is not the official, or people do not speak English so much, but they have a very high proficiency. So that those were our 6 countries that we selected to collect tweets from. And on the right, it will give an idea about the number of geotag tweets across these countries over the whole period. And as you can see that during the period of 2015 to 18 and 19, there was uh, most people were talking about this new type of modes like urban air mobility or flying cars, and then it got reduced over time over this 2019 to 2021 phase. To show you about the results, what we got from the sentiment analysis. So the first one is the result for the what we also call as the classification model. So the first one is from the support vector machine model, and the second one is from the BERT model, which is also can be called as large language model or transformer based model. And this is the result from a classic confusion matrix that we always use. To give you an idea of what is a confusion matrix is same as, so I'll explain it one by one. Let's focus on the confusion matrix charts at the left, like what you can see as the blue check boxes and then this orange or brown check boxes. So for this particular task, we had 4 categories, what you can see as 0, 1, 2, and 3. 0 was negative, 1 was neutral, then 2 was positive, and 3 was off topic, like 4 types of tweets. We wanted to classify. So just think about what we learned in our last session, that we talked about we can use this supervised learning where you have various classes or categories. So in this case, what are our categories? Different types of tweets: positive, negative, neutral tweets. These are the categories. And we train the model. In this case, the machine learning model is support vector machine. So we train the model, say, with 1,000 data points. And then for the rest, say 14,500 of rest 15,000 data points, we ask the model to predict it. That's how we got this confusion matrix. I mean, for example, this confusion matrix is generated when we test it on a very small holdout sample. And after this, we get enough prediction accuracy. We use that to predict for the rest of the data points or rest of the tweets. What we want here is that we want most of the data points to fall in the diagonal. Why diagonal? Because diagonal represents that your true level and predicted level is the same. That means you are correctly predicting it. That what it means, that when your predicted level is same as the true level. So you can see if you follow the diagonal of these charts, you will find that whenever true level and predicted level same, that is the one you will find in the diagonal. So we want to maximize the diagonal, or you want to have more and more data points in the diagonal, because for the all other points you can find on the chart, they are kind of misclassified. So we want to reduce misclassification and we want to increase the correct classification. So as you can find that in case of support vector machine, we attain the accuracy of almost 0.72. In case of BERT, we attain the accuracy of 0.75. So BERT was the better model in terms of prediction accuracy. And we also did another interesting thing here is that, for example, when we are training the model, we did not have same number of data points while training, because you can understand, say within 1,000 tweet, maybe you will have 500 tweets which are negative, 300 which are positive, and very few which are say neutral or off topic. But when you are training a machine learning model with help of a data set which is not balanced, the machine learning model will actually learn the pattern for the majority class. What is a majority class? Majority class is the class for which you have maximum number of training data points. So your model learns the pattern of the majority class better, but not for the minority class. That means for the class where you do not have enough data points. The solution for this problem was to balance the data set. So we use the translation based balancing to have a more balanced data set, which was used for training these data points. This balancing was done for both support vector machine and BERT. So another interesting point is that we learned about the machine learning, and I gave you the example of the support vector machine. So BERT is similar to machine learning in terms of uh, like certain aspect, but it is very different when it comes from its algorithm or like the inherent methodology, because BERT is more transformer based. So it is out of the scope for today's tutorial, but I'm just trying to give an idea about this BERT model, because now we are more and more moving towards this large language model or transform based language model, which is an advancement as compared to the machine learning models too. But at the end, we found that this BERT model, because of its encoder only structure, this it's quite a pre-training approach. It was already pre-trained as compared to machine learning. That the difference means that in machine learning, as I was given the example, I need to train the model fully by myself. In case of BERT, it comes with certain pre-training. What I do as an analyst, I try to fine tune the model. If I draw an analogy, it's like, say there are two students in a class. One student does not know anything about a topic, and you try to teach that student from scratch. And then there is another student in the class who knows the basics. For example, he or she knows how to addition, how to do add, how to subtract or multiply. You just need to show him or show him or her maybe a little bit of advanced calculation or Bodmer's rule. Then at the end, you make them appear for the same exam, and you check who performs better or who performs not so good. So that was the difference between SVM and BERT. So SVM was the one where we taught the model or trained the model from scratch. For BERT, it came with certain pre-training. We fine-tuned the model. And the main or the key advantage of BERT is that in case of this natural language processing, it tries to understand the context from the both side of sentences. So it's not very important feature when you're trying to understand this the prediction accuracy, but I just wanted to mention it to give you a good idea about how a BERT is superior as compared to the support vector machine model. Now we are going to our second task, that we mentioned that we understood and we now have a sentiment model. So we can classify the tweets to say it's a positive tweet, it's a negative tweet, or it's a neutral tweet. Then, but we at the same time we need to understand how this polarity, like positive, negative, or neutral, how it changed over time, to get an idea whether it can capture the real life events well or not, because that's what we want. We want to understand that whether real life events, for example, say this Uber or Joby Aviation or other manufacturers made some demonstration or they announced some big plans, whether those big plans made some effect on public sentiments or opinion. We want to understand that. So we found that yes, our model can capture the real life events quite well, and both the positive events and the negative events. For example, in 2017-18 period, you could find that there was a very positive spike, uh, which can actually be attributed to various ambitions plans that were announced by electric aircraft by Uber Elevate. And in 2015-16, you could find the red one spiking. This could also be stemming from few drone related accidents that happened during that time. So there were possible public concerns regarding the negative externalities of those events. But still, if you remember our research question, we still do not have idea about the spatial differences. Is it same in India and same in USA, or it is quite different? So for that, we needed to do a spatial heterogeneity analysis that we do through K-means clustering. So the last one, you got an example of supervised learning, right? So where you train the model, you had these 4 classes and you train the model. So now remember, within the unsupervised category, I talked about the K-means clustering, where when you do not know the underlying structure of the data points, you give model all those data points, then you try to understand the underlying structure. K-means clustering, what we used here, is one example of that. So what we feed into the model, our input was this tweet sentiments, number of positive tweets, number of negative tweets, number of neutral tweets for all these countries, all these 6 countries. And we wanted to understand whether these countries can be grouped into various clusters or not. So we found that actually these 6 countries can be grouped into 4 different clusters based on the number, or here we have presented it as a percentage of positive, negative, and neutral tweets. So what we found, the real life example or real life implication of it is the first cluster, which comprises US and Australia, which are more car dependent and they have a society which is more uncertainty accepting. So we found them to have a very high positive, at the same time very high negative. So basically they are more opinionated about this new technologies. Whereas in India, you will find is average positive, not so negative, so low negative and very average neutral. So it's more towards the neutral end of it, which is very plausible considering in India, still these of kind of futuristic modes like flying car are quite distant horizon. So we people here we do not have very clear idea how it will look like when it comes into reality. Will it be only used for the logistics sector, or will it be used for passenger mobility too? What will be the safety guidelines? What will be the operational guidelines? We do not have much idea. So it's more like we have very neutral opinion, and sometimes we have very average positive opinion based on the reports and news we see in the international media. On the other hand, Germany, you can also find very high neutral and both low positive and low negative, but the reasons could be quite different. It's because of their socio-structural nature, and at the same time their awareness and their, for example, very higher incubation rate, where they are taking a very pragmatic approach towards this adoption of this new or these futuristic modes. So once we perform this spatial and temporal, we went to the topic modeling. As I explained, that now we know the timeline or the temporal heterogeneity. We also know how it is different across various countries. We need to understand what are the drivers, like what made them positive or negative or neutral. So that's what we did through dynamic topic model. So this is an example of when we perform dynamic topic model, we got various topics, and for example, this excitement, industry innovation, or say unmanned aviation systems. So, and for each categories, we have got a set of keywords with their keyword weight. which helped us to understand what are the key features which are shaping that particular topic. So the summary of findings is that we've observed industry innovation system, unmanned system, tasting, excitement. These are the key global topics. That means these are the topics which are present across all the countries, all the clusters. But there are two interesting things. Is first that it is important to understand that there could be same topic in two clusters, but the ranking of that topic will not be the same. For example, in the USA and Australia cluster, we observe that they are more excited about this thing. It's a pure excitement. So excitement is the number one ranked topic in US and Australia. But as you can see, when you come to the India, excitement is the least important or lowest ranked topic. That clearly shows that in India, people are not excited, but it's not as simple as like saying they're not interested. It's more like it is because of the distant policy horizon, and also because of our affordability, because of our different socioeconomic background. We are we're not as excited as this USA people or Americans about this new futuristic mode. The second thing is that it will give you an idea about how different topics are present across clusters, and if some topic, for example, this industry innovation and testing, it is present across clusters and it is always the top ranked, or in case of cluster one, this second top ranked topic, that will give you another people across cluster are very much interested, be it India or be it USA. There is a similarity there. People are interested how industry innovation is happening in this sector, and whether there are this testing and demonstration happening, because people want to understand what will be the real life mobility benefits of this. Will can I use these flying cars to reach to a destination quickly, or if it takes me say 15 minutes instead of 1 hour, will it cost so high that I'll not be able to use it say frequently? So that is very important for people, and that's why they're interested to know how industry is making progress in this sector, and what if they're making some announcement or demonstration, they are really interested about it. So that gives an idea about the global topic also. So furthermore, we analyze the country specific trends to understand how these things are and why, what are the key driver that I've been talking about. For example, in case of US and Australia, we found that the excitement went up when there were key developments happening. For example, some announcements, some public demonstration. But at the same time, we found that because of the policy bottlenecks, the initial interest kinds of fizzed out at the later stages of the last decade. And then this delayed layout led to the excitement loss. So what can be done in terms of policy implications or policy perspective is that you need to have a very clear policy timeline or regulation timeline. Then you need to have people on board so that they are aware about this, so that you can actually manage that expectation for sustainable or for kind of planned rollout of these new modes. And then you need to integrate this urban air mobility with the existing travel alternatives. Another example I wanted to give about India, where I've all been talking about it, that for the distant horizon and the social infrastructural context, we found that they're quite low excitement. But at the same time, you could find that whenever there was a policy rollout, for example, drone policy rollout happened, it created excitement amongst the people. So people wanted to know about what are the important aspects of these drone policies, how it can be used, or whether it is only for the logistics sector, or whether these kind of policies are going also to expand to the passenger mobility sector or not. So in case of India, our policy suggestions were that in addition to the innovation, you need to actually have a good amount of demonstration so that public knows the actual benefits. And of course, we understand that urban air mobility or flying car will not be for all, but you need to have this demonstration to know who are your target uh, group, as I explained. And then policy need to be more matured. For example, we just have the drone policy now, so there need to be very clear policy guidelines. And then, of course, the integration of UM, as was the case for the USA. But at the same time, because of our unique social infrastructural context, we also need to prioritize the inclusivity part of it. So these will be the future extensions. I'll not go much into detail, and I'll actually now focus into the second case study that we used. This is also related to the another large scale passive data we collected from the Facebook data. So from the Facebook data for good program, we got hold of the mobile GPS data set that gives us the location data for the people, anonymized location data. And with help of that, we tried to understand that how people moved during the time of natural disaster. And we took the example of storm Ewan in the UK. So when we are talking about these extreme events, for example, hurricanes or floods or wildfire, we need to understand that first of all, it is not necessarily that one event will happen at a time. There could be multiple catastrophic events at the same time, and even multiple non-catastrophic events happening at the same time can lead to a crisis. For example, say there's a very heavy rainfall and it caused flood, and then for that there is a closure of train network, road network, bridge collapsed. So all of the together, this crisis and the secondary crisis which are after effect of it, like this bridge collapse or stoppage of train services because say trees fell down, this crisis and secondary crisis together will make a poly crisis. That means a systemic level of crisis, very a large scale crisis, so which need to be understood quite carefully in the context of natural disaster resilience and adaptation. Second one is that we mostly focus into the large scale disasters, for example, hurricane or very intense cyclone. But we often uh, ignore the effects of these non-catastrophic events. For example, very strong or deadly storms. But with global warming, we know that these kind of non-catastrophic events like small scale storms or these small scale cyclone maybe or depressions, these are becoming more and more frequent. That means we actually will see more of these non-catastrophic events which together can create bigger crisis than a very big catastrophic event. So we need to be prepared for this non-catastrophic events too. Why? Simply because the example I gave, these are some pictures of what kind of infrastructure disruption that can happen as a result of this poly crisis. For example, that could be property damage, link closure, that means stopping of this or breaking of collapsing bridges, uh, breaking of this train network. Then there could be internet and power blackout, flooded roads like that. Lastly, when we talk about the resilience or adaptation, it will not be same across various region and various group of people. The simple reasons are we are quite different in terms of our needs, in terms of our background, in terms of our access, everything. So people who are vulnerable will actually face the brunt of these events more than people who are better placed than them. So it will for to devise an equitable plan, resilience plan or adaptation plan, we need to understand how heterogeneous these responses it will be from the people when it comes to talking about this infrastructure disruption. So in this case, in particular study, we processed Facebook dataset, and from the Facebook movement data that we collected, we generated the total flow index for a city in Scotland. And within this flow index, we had two types of flow index. One is interzonal, another one is intrazonal. So with help of both interzonal and intrazonal, we created a spatiotemporal visualization of resilience or impact curve, which finally led to the aggregated impact analysis. And when I say impact, I mean resilience impact analysis. So once I got the aggregated impact analysis, I used that to profile the mobility resilience for different socio-demographic groups. And there we used unsupervised clustering. Time series came in, very similar to what we used, but we had this additional time series one in this case, which helped us to profile the clusters. So let's start with how we analyze the flows and what we got. So what we found is that there are various phases when we plotted the mobility flows. And one thing I should add, that from the Facebook data, we had the anonymized flow information during the crisis period. That means during when the storm made the landfall, and for the baseline period, that means for the normal period. So with help of it, we generated this intra and interzone mobility flows. And we observed that in case of intrazonal flows, it increased during the landfall day. We find a quite contrasting behavior. So intrazonal flow, that means flows happening within a zone, that increased on the landfall day. While the interzonal flow, that means flows happening between two different zones, that decreased on landfall. But if you follow the recovery or the stabilization period, we'll find that intrazonal flows actually stayed below baseline, whereas interzonal flows actually went above the baseline. So you're finding very contrasting nature of human mobility during the landfall and then during the recovery phase. What we created this interzonal and intrazonal flow index maps, and we took the example of Edinburgh City, which is the second largest city in Scotland, and we plotted this interzonal flow index for all these 10 days, which are my study period from 24th January when the landfall happened until 2nd February. So this will give you an idea about how we calculated the intrazonal flow index, but I'll mainly focus on the key observations here. So in this case, So in this case, we found that on the landfall day, as I mentioned, that interzonal flows actually decreased, and almost you could find that interzonal flows reached almost near to zero. That's why you can find it very much all red across the city. From the next day onwards, it tried to regain the pre-event equilibrium. That means it almost got back to the normal phase, and over the next time, the stabilization phase, it actually went above the baseline. Whereas for the other one, that's the intrazonal flows, we found the opposite trend. That is, during the landfall day, interzonal flows were higher than one. That means it was more than the baseline. I'll explain the reasons later on, but I'm just now explaining the observations. And then for that stabilization or recovery phase, we found that it actually came below the baseline. So you can find this kind of a balancing act between interzonal and intrazonal flows that's happening. So if we explain now the intrazonal flow index, and we could find the various what I should say, is like various phases. What we can classify them as like impact phase, recovery phase, and stabilization phase. So very distinct three phases that we can find. So the 24th January was the impact phase when the landfall actually happened. You could see the inter zonal flow index is around 0.19. It is quite high, but important thing is here the application of clustering technique. So here we again used that time series k-means clustering to understand how it is different in nature. So let's again go back a bit to what we learned in our first session, that when we have data points, we do not have any label, that means unlabeled data points, and we want to understand whether we can group them into distinct clusters. Then we used unsupervised machine learning techniques. In this case, we did the same. We did the same for understanding the clusters in terms of countries. We also did the same to understand whether there are clusters. With the clusters mean intermediate zones within the Edinburgh city. And we could find there we could have two clusters. What were our inputs? Our input in this case was this flow index across all the 10 days. Important point is that for the last example or last case study that I was showing, we did not have data points across like time series data points. In this case, we have time series data points. So it is like different flow index value for all 10 days. That's why we use time series k-means in this case to identify these two clusters. And we found that these two clusters are a little bit different in terms of their resilience behavior. As you can see, for example, the cluster 0, where there are 33 intermediate zones, IZs, you could find that it almost stayed very close to the baseline. Baseline is the dotted red line that you can see. So it almost stayed very close to the dotted red line or baseline. Whereas for the cluster 1, you can see that it showed a bit different behavior, different resilience behavior, because here the flow actually went quite above the baseline. And this is also for just 12 intermediate zones. So majority of the intermediate zones fall in cluster 0, whereas 12 intermediate zones fall in cluster 1, which showed a little bit of different behavior, that the flow index went quite below the baseline or normal behavior, and then gradually again came back to the normal at the end of our study period, what we're calling as the stabilization period. Let's see if we can do same thing with the intrazonal flow, and we were actually able to find also two clusters for intrazonal flows. If you observe closely, these look more similar. So as compared to the interzone, the difference is quite clear between cluster 0 and cluster 1. In case of intrazone, the difference is not very clear, or I should say that these two clusters are behaviorally, in terms of resilience behavior, are behaviorally quite similar to each other, but still there are a subtle difference. For example, in cluster 1, where we have 26 intermediate zones, we could find that during the stabilization phase, cluster 1 actually went a bit below, comparatively more as compared to cluster 0. So our final task was that once we identify these clusters in terms of flow index, so we now know how different types of flow pattern we could observe with help of our data set and with help of this unsupervised clustering. We wanted to link it to various aggregated socio-demographic parameters of those intermediate zones to see whether there are any relations for this heterogeneous flow responses with the socio-demographic or deprivations index. And we could actually find that people who has car or people who drive cars are the ones who try, or rather who belong to those intermediate zones where there were more number of flows happening during the stabilization phase. So that kind of leads to the inference that when you have your own vehicle, then you try to make more number of trips, or you kind to do this catch up thing after you are struck by this kind of non-catastrophic events. But if you are dependent more on public transport, because when this kind of storm events happen, it takes a couple of days for this train network or bus network, because of the road closure or say tree falling on the train tracks or some other issues. So it takes couple of days to for them to get back into the normal. So when you are dependent more on the public transport, then for it takes more time for those people to get back to their normal routine. Same time, we found that in terms of deprivation characteristics, we found that cluster 1 is associated with lower number of people who are income deprived or employment deprived. So we are also saying that in case of those people who are more income deprived or employment deprived, they are the ones who are more likely to make this preemptive trips when on the face of this incoming disaster. What are preemptive trips? For example, just collecting some groceries or some emergency materials to be in a safe place just before, because they are the ones who are the poor people. They are the ones who do not have enough backup, or they do not sometimes have shelter. So they are the ones who are more likely to have this preemptive activities when there are imminent this kind of natural disasters or catastrophic events happening. So in terms of the future extensions, we're planning to see whether we can use this data set in conjunction with other data sets, other location rich data set, and whether we can establish this social inequity or inequality and multiple deprivations in a statistical modeling way. So that's all from my side for today's presentation, and I'm open to any questions now, and feel free to email me if you have any questions, and I'll be happy to answer them to you. Thank you all, and thank you the organizing team for this great opportunity.
If the participants want to discuss with sir, open to all for 5 minutes.
Good afternoon, sir.
Good afternoon.
Yeah. Firstly, thank you for the wonderful presentation on travel behavior and modeling. So my question was sir, in supervised learning techniques, we have like in classification, like as you have discussed, there are so many methods like logistic regression, decision trees, SVM, random forest, KNN methods. Which method, like where when to opt? Like I mean to say, like which method to be chosen for what type of data set?
So as I was explaining, could you elaborate a little bit? Like, what do you mean by what type of data sets?
Like, I mean, which method to be chosen? Like, if I go for logistic regression, decision trees, SVM methods, like, suppose if I have a particular data set, which is a method which is appropriate for that data set? Like, how to choose which method is suitable
So,
for that type of data set?
so I'll say that as I explained that in terms of labeled data or unlabeled data, we have this supervised or unsupervised method. But when you're use, so one of these methods is like you try various methods, because each method has its own advantages and disadvantages. So you try various methods. For example, if I take our case study on the Twitter dataset, so SVM was the one which performed best, but it is not that we only estimated SVM model. We also tried random forest. We also tried naive based model and other models. So based on the task, say you want to do classification task, so then you'll use obviously supervised technique. So within supervised technique, you need to perform various models because it is completely data driven. So you might find that SVM is performing better in one case, but it might not perform as well for the other type of data set. So for example, in case of text data, usually we find that SVM and random forest both perform well, but you need to apply both of them to see that for your case, which one is actually performing better. Maybe SVM will perform better for your case. And another important point is that hyperparameter tuning. That for each of these machine learning models, you will have a set of hyperparameters. So you need to tune those hyperparameters and test those models to understand that which one is actually suitable in your case. I hope it helps.
Yeah, thank you, sir. Sir, and one more
Thank you.
query, like, how to identify whether we have any noise in our data set, and like, what are how can we eliminate it from our data so that we can increase the accuracy of our model?
Yes, so there are different methods. I can just share that with you over email, but I'll give you the example of the text data. So within the Twitter dataset or text dataset that we had various tweets which are generated by chatbots, which were various promotional tweets. So for the chatbot tweets, we filtered them out. For example, the promotional tweets, we tried to classify them as off topic because they are not from the real people. So from context to context, we'll have different methods to find these noises within the data set. And based on that, you can try to remove them. And basically, and obviously before, for example, if you have a numerical data, you try to plot them at the beginning and see whether they are following any visual pattern, which can be used as a basic filtering technique for you.
Okay, thank you, sir. Thank you for your time, sir.
Okay, thank you.
Participants, if you have any queries, you just mail to the sir. Because of the time constraint, we'll conclude this. I'm inviting Anita ma'am to conclude the sessions. Thank you, sir. Thank you for your valuable time and it's good
Thank you.
session, sir.
Thank you.
Dr. Erwin, it is my privilege to deliver the vote of thanks on this special session. On behalf of the department and all the participants, I express our heartfelt gratitude to Dr. Ishan Madhuri for sharing his valuable insights with us today. Your talk on travel behavior, modeling, and sustainable transport has been both enlightening and inspiring, giving us a deeper understanding of how data-driven approaches can shape the future of mobility. We extend our special thanks to our Honorable Vice Chancellor for the continuous encouragement and support in organizing such knowledge sharing sessions. Our sincere gratitude to the Department of Civil Engineering and our respected head of the department, Dr. Deepankar Roy, sir, for guiding us throughout the planning and successful execution of this event. I also wish to thank our faculty coordinators, organizing committee, and technical team whose efforts ensured the smooth conduct of today's session. Finally, a heartfelt thanks to all the participants for your active involvement, which made this event meaningful and engaging. Once again, we are truly grateful to Dr. Ishan Baduri sir for his time and expertise. Thank you, sir. Thank you very much, sir. Thank you all.
Thank you.
Sir, thank you, sir.
Thank you. Thank you, everyone.
Yes, sir.
Thank you.